So, ladies and gentlemen, our next topic is a much anticipated awards ceremony. It begins today with the EPMA PM Thesis Competition for 2016. Before announcing the winners, I would like to thank Huguenas AB in particular for once again sponsoring the prizes for this prestigious thesis awards. The awards will be presented by Mr. Gunderman. Firstly, we are delighted to announce that the winner of the 2016 EPMA PM Thesis Competition in the Diploma Masters category is Mr. Uriel Tradowsky, who is studying at the Technical University of Berlin in Germany for his dissertation, Selective Laser Melting of Aluminum Silicon Magnesium Alloy, Influence of Post-Processing on the Microstructure and Mechanical Properties.
Dear audience, my name is Uriel Tradowsky, and I'm more than happy that my work was selected for this award. The title of my thesis is Selective Laser Melting of Aluminum Silicon 10 Magnesium, Influence of Post-Processing on Microstructure and Mechanical Properties. Talking about the frame of my project, I was a master student of materials science at the Technical University of Berlin, where I was associated with Professor Reimer's group. Then, in 2015, I was moving to Birmingham to work with Professor Atala and his Advanced Materials Processing Lab. My project scope. I received aluminum silicon 10 magnesium powder, and I performed selective laser melting to obtain samples. With these samples, I did post-processing to compare with as-fabricated selective laser melted samples. One batch of samples was hot isostatic pressed. A second one was artificial aged by a solution and aging heat treatment. And a third batch was first hot isostatic pressed and then T6 heat treated. With these 4 batches of samples, I performed tensile testing and microstructure characterization to compare the different conditions. I received a lot of very interesting results. Obviously, I cannot go into detail here. However, on the right side, you can see a graph. You can see that the as-fabricated selective laser melted condition was best in terms of the ultimate tensile strength, and that the HIP plus T6 treated condition was best in terms of the yield strength. If you want to see more details, there is a paper published containing the results of my thesis, and if you want to read further, the thesis is available on request. After finishing my project in Birmingham, I moved back to Berlin to work for a company, Photon Laser Engineering. At this company, I am responsible for the powder-based processes, such as laser cladding, and I am involved in various manufacturing and research projects. At this point, I want to thank the EPMA for this award, and say thank you to Professor Atala in Birmingham, Professor Reimers in Berlin, and Dr. Noriko Ried. Thank you.
Thank you for your excellent presentation and for the synthesis performance. The winner of the thesis competition in the Doctorate PhD category is Dr. Elena Bernardo, who was studying at Universidad Carlos III de Madrid in Spain for her thesis, optimization of liquid phases for sintering low alloy steels, effect on microstructure and dimensional control. Please, Dr. Bernardo, the floor is yours.
So good morning to everyone. I'm really happy of being here. Thank you for the committee for the award. And really thank you to my two supervisors, Mónica Campos and José Manuel Torralba, for their guidance and their support, and for teaching me more than science. I've been really lucky because I could have worked within the frame of the Höganäs chair. So Ulla Lidström and Robert Frickholm from Höganäs, Christian Gierl-Meyer and Herbert Danninger from TU of Vienna, Alberto Molinari from University of Trento, and Eva Drudrova from Košice, thank you very much. I think you are the perfect example of how it is possible to push forward this technology from science. And last, thank you to Raquel de Oro for her help and commitment during this work. So now we can move to science. And I will briefly say what we have done. So we have designed new master alloy compositions with a low melting point to create a liquid phase during sintering. So we know that we have a liquid, so the question that we pose is, are we able to customize the properties of the liquid to control the dimensional performance and the microstructure of our steels? And we can say that we can do it if we pay attention to the solubility relation between the liquid and the solid phase. So based on this solubility, we have two design possibilities. We can have a low dissolutive liquid, which has infiltrating properties, so the liquid creates and rapidly penetrates through the contacts. But also, we can have, on the other hand, high dissolutive liquids with non-infiltrating properties. So this means that the liquid will be created, but will not be able to penetrate and distribute. Let's see which consequences that this has. First consequences, we can feel it in the microstructure. So with a low dissolutive liquid, we can create completely homogeneous microstructures, which is this case. This reminds us of what pure copper can do. But on the other hand, we can also design heterogeneous microstructures with a high dissolutive liquid, which is this case. The master alloy leads us to the liquid form, but it tends to stay where it is created because its mobility is completely reduced, and this gives us these heterogeneous microstructures. The second consequence, we can feel it in the dimensional behavior of our steel. We expect that we will have a swelling effect when the liquid forms and penetrates through these pores and channels. And we can feel it here. We can quantify this swelling effect with dilaptometry, but what it is interesting to see is that if we have a high dissolutive liquid phase, we can reduce the amount of this swelling. And we can reduce it almost to 1/3 of the value of what we obtain with a low dissolutive liquid phase. More interestingly, we can design liquid phases with different sensitivity to the solid that they are wetting. Here, and this will, of course, directly affect the dimensional behavior of our steels. Here, what we can see is that if we have a low dissolutive liquid phase, only under reducing conditions, we can decrease the amount of swelling that we have. So, in practice, what we have developed is a methodology of designs of master alloys, taking into account this solubility from the first step of the designing of the composition. So when we are tailoring the composition of the liquid phase, we can also design the solubility condition in between the solid and the liquid phase. This, of course, we will always We will always experimentally validate it, but what it is important is that we can adapt the behavior of our liquid phase to the final requirements of our steel. So for instance, if we go to a higher, for a liquid with a high dissolutive capacity, we will aid wetting. We will always create heterogeneity in our microstructure, and we will always promote densification in our steel. So sorry, this was really brief, but that's the time that I had. Thank you very much for your attention.
So thank you for this excellent presentation and for summarizing 3 years into 3 minutes.